From the very first time you walked into my classroom, we started to talk about this idea of efficiency. And up till that point, it was simply just a matter of writing good, clean code and trying to make sure that the choices you made were good choices in terms of how much space is taken up, how often you do certain actions, and how to control when and where to define variables and things like that. And that's important. But there's more to the discussion. So now we introduce this idea of algorithm time complexity, but really it's just the time aspect when we talk about that space-time efficiency check. How much time does it take for our algorithm to run in general? And it's that in general aspect that really matters, because we can look at a single algorithm and say, well, it runs on it finds the the maximum value inside of this array in 2 seconds, but well, obviously 2 would be really big, but the point is that's not really a good accurate measurement, because really we want to think in large scale and in big terms. What if it's not 10 elements in the array? What if it's 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000? We want to think about how efficient is that algorithm as the number of elements grows to infinity. What does it generalize to mathematically? And that's the goal for today. By the end of the lesson, you'll be able to analyze an algorithm and know how to approximate its running cost on a CPU. The purpose of this is to be able to compare multiple solutions to the same problem and make an informed decision of which one to use. It's often a choice between speed and memory. However, you're going to see that some algorithms vary on other things. So for example, some algorithms, they're really fast on big data sets. Others are really fast on small data sets. And sometimes they're even faster than those ones that are supposed to be quicker than them. Because on small data sets, they can operate through the data a lot more efficiently. You're going to see a few examples of this. So your choice may then depend on ease of implementation. So sometimes the speed of something is not your priority. It all depends on what your priority in the organization that you're working in really adheres to. So if you're making a program for a device that has very limited memory, maybe something like a phone, memory may be more important to you than processing power. And if you're working on something that has infinite resources and you're just looking to deliver the best result possible at the end, well, you may have to actually take both things into consideration and trying to find that happy medium where both things are optimized as much as possible. So we got to look at a few terms, new terms that we haven't seen before, just so we can understand what this whole discussion is about. So the idea of time complexity. This is roughly a measure of the number of operations a CPU will perform during a given algorithm and a given size of input data, n. N is the general term we're going to use for the number of items we're working on. So for example, how many operations does it take to sort a set of 10 numbers? So in that case, your value of n is 10. So it's always about the input size. How big is our input size? So we're going to look at a lot of different time complexities. And what you're going to see is that over time, they're going to come out to be some form of function that represents, as the number of elements grow, how many operations are we taking? And you can see in this colored graph here that there's different expressions that are going to result in different results. So for example, some of these things, doesn't matter even how many elements you add, they're still just as efficient and do just as little operations on them. Whereas something like over here, this big O of n factorial or 2 to the n or n squared, things like that, you can see that it doesn't take very many elements at all for it to really spike. And that's a big problem. We really need to try and avoid these situations. So, time complexity, that measure. Asymptotic analysis. So this is the process of actually determining the time complexity of an algorithm. So, and when we do this, our whole mindset is how efficient is this relative to the input size as that input size increases towards infinity. So if you look at this graph over here, we're really looking and analyzing how many operations are happening as the number of elements increases. So for example, the nice straight line here that you see here, that one happens perfectly proportional. So it means for every one element you add, it adds one more operation. So that's a perfectly linear line, which is why we call that a linear time algorithm. And then finally, we get into this idea of big O notation. So the mathematical notation used to describe the worst case scenario of the algorithm as n approaches infinity. So commonly we write this as big O, and then inside the brackets, some function of n. So in here we have big O of n squared in this example, and that's going to be this line right here. I'd tell you the color, but I'm colorblind, so I don't know. Blue, purple, green, I don't know. Either way. So point is that we have three new terms that we need to use. We got time complexity, asymptotic analysis, and big O notation. Let's see how we can apply these things. So how do we actually do this? It's typically just an act of analyzing the code that's sitting in front of you. You got to break it down into a mathematical formula. And then we're going to organize and reformat that formula until it becomes as simplified as possible for the value of n. We're going to look at it and we're going to say, well, what is the most important term in this function? That's the one we care about. So let's try a simple one. On the left-hand side here, we have a very straightforward algorithm that just adds up the sum of an array. So obviously the function is called sum. Inside of here we have one command that sets the result to 0. Then we have a for loop that loops through the entire array, and for every element of the array it adds itself to the result variable, and then it returns the result. So we have 4 lines of actual instruction here. Now that being said, line 2 actually has 3 different instructions on it. So let's come back to this. So our first step is to try and break this down line by line, all right? So we're trying to determine a function f of n for the algorithm given that array size of n. We don't know how big n is, and that's the whole point. We want to look at this like we don't know. How efficient is this algorithm going to be in general? So for this, we're going to say the cost of any one operation on the CPU has a value of 1. And this will keep our function nice and simplified. So when we're talking about what f of n is simply just a sum of all the operations. That's it. So if I had an algorithm that was just 3 lines of code, well, that would take 3 commands. And it wouldn't matter how big the size of n would be, because if it's just 3 lines of code that's just linear instructions, if n was infinity, it would still just be 3 simple instructions. It's when we start to introduce things like loops and stuff like that that changes everything. So let's start to break this down. For each operation that you see here, how many times does it execute relative to the size of n? That's the question you want to ask for every single line. So this first line here, int result equals 0. How many times does that operate no matter the size of n? If data is 10 elements or data is 10 million elements, how many times is that line of code going to run? It's going to run exactly 1 time. It's outside the loop. It's going to happen once. Okay. Then we get into line 2. Now, this is a little interesting. So this one will iterate n times. So we see it starts at 0 and it goes all the way up to, but not including the length. So that's the entire size of the array. And the array is of size n being our arbitrary number here. So what that means is that that array is going to iterate n times. Now, looking at this, there's actually 3 instructions on this line. We have the assignment statement, which is I is equal to 0. That happens once at the very beginning of the loop. And then we have these two, the next 2 statements, which is the comparison and then the increment. These 2 things happen, they each happen once for every iteration of the loop. That means they're each going to happen n times. But we're just going to ignore that for now. So as it says here, although there are instructions on this line, we can simplify our work by just treating this as a tool to tell us how many times line 3, all the code inside, is actually going to execute. So going forward, when we're looking at these loops, we're going to look at all the different lines inside, and we know that every line inside of the for loop is going to operate or execute the number of iterations that exist in the for loop. So in this case, n iterations. So that means line 3 is going to execute exactly n times, once for each iteration shown by line 2. Okay. And then finally we got that line 4 at the bottom, and again, that's outside the loop. So it's going to execute exactly 1 time as well. So we have 1 time for the first line, we have n times for line 3, and we have 1 time for the last line. So bringing it all together, we have 1 plus n plus 1. So our function f of n is equal to n plus 2. Okay. So what this means is no matter what we put in there, no matter what the data set is, if the data set is 10,000, it's going to be 10,000 plus 2. If the data set is 100, it's going to be 100 plus 2. So 102, 10,002, 10 million and 2, 10 billion and 2. How significant do you think that 2 is? And that's where we boil it down to generalize it, because there's some of these terms that just don't matter. As n grows to infinity, that 2 just becomes less and less significant. If n was 1, well, that 2 is very significant. If n is 1 trillion, that 2 is nothing. So we're nearly complete. We got one more step. And that one more step is actually 4 steps. So the asymptotic analysis. So this is when we take that function, that f of n, and now we're going to follow 4 steps. And these 4 steps are going to bring us and finish us off at our big O notation. All right. So now we're going to consider what is the most important factor of our function as n approaches infinity. Looking at n plus 2, looking at just the n plus 2, what is the most important part of that function? Well, I'm sure you already know what that is, but let's break it down. So the first step, put the function in standard polynomial form. So linear, quadratic, so if it's an n squared, n cubed, that kind of thing, put it in standard polynomial form. We already did this by combining our like terms and adding our constants together. So we had 1 plus n plus 1, and we combined those and made it n plus 2. Makes sense. Step number 2, sort your terms by the rate of growth. So if we had an n squared in there, that n squared would have to come before the n. But we already did this because this is a very simple function. Only keep the one that is bigger, which means if you have something like n squared plus n, you throw away the n. Why? Well, I challenge you to do something like, take your algorithm. Let's say you have an algorithm that's like n squared plus n plus 5. And if n is 10, that means you have 10 squared plus 10 plus 5. So you have 100 plus 10 plus 5. Now imagine if that was 10,000. Now you have 10,000 squared, which is an astronomical number, plus 10,000 plus 5. Even that 10,000 is insignificant relative to that 10,000 squared. So we don't care about it. So we just toss it away. So only keep the one factor that is bigger when n approaches infinity. All others become completely negligible relative to n. So we only have one factor in our equation, which is just the n. Then finally, the final step is take away any constant values and coefficients of n. Because if I have 2n squared, that 2 is insignificant as n approaches infinity. If I have, 10 trillion or 20 trillion, it doesn't really make a difference, right? As that n grows, that 2 becomes less and less significant. So we toss it away. So that's the coefficient, gone. And then, of course, any constant values like that plus 2. Well, 10,000 plus 2, 10 plus 2, 10 billion plus 2, that plus 2 is irrelevant. So we throw it away. So all constant values and all coefficients, gone. So what we end up with is f of n, which is equal to n plus 2, just becomes n. So now, now that we're down to that just n, this means that our time complexity is big O of n. The term we use for that when you see anything that's big O of n is a linear algorithm. What that means is for every value, for every input that you add on, it's going to create one more operation on the CPU because it's completely linear. All right, here's a little bit more complicated one. So this one, you got to look at the comment here. So the data is a square 2D array. Square 2D array. That means that it's got the same number of rows and columns. So it's n by n. So all this function does is add up all the elements and then display the element on the screen as well as the final sum. So looking inside of here, we have we got to break it down in the exact same way, right? So if we look at anything outside the loop, we know that's only going to happen one time. So that means that lines 1 and 6 are exactly 2 instructions. No matter what this algorithm does, those lines represent 2 instructions. Okay, let's get into the real nitty-gritty though. Line 2, this is a loop that iterates how many times? Well, n times, because we know that our array is a size n by n. So that first loop is going to go all the way up to n times. Okay. The next loop also goes n times. We can see it has the exact same setup. So we have a loop within a loop. Okay. But inside of here, we have 2 lines of code. Now, on their own, they each take 1 instruction. So that's a total of 2, right? 1 plus 1 is 2. But how many times will each of those instructions execute? Well, let's think about that. They're going to loop exactly n times for the j loop. Okay. But the j loop, it loops n times for the I loop. Now, if we do the math on that, that means that we have n times n iterations, or n squared iterations for line 4 and 5. Really, all we do is we take the number of iterations of the first loop and multiply it by the number of iterations of the second loop, and that's how many times everything inside is going to actually operate. And we have 2 instructions in there, so there's 2 of them in there, so we end up with n squared times 2 instructions. Okay. So now we got to put all this together. We have lines 1 and 6 that are 2 instructions, and then we have the inside of the loop, which does n squared plus 2 instructions. All right. So what do we end up with? We end up with 2 for the 2 instructions plus n squared times 2. All right. Now that we have this, it's time to do the asymptotic analysis. Let's bring it all together and do the 4 steps. Step number 1, put the function f of n in standard polynomial form. This means group our terms and put everything in standard format. So we end up with 2 plus 2n squared. So we combine the like terms. Well, the next step says sort the terms by their rate of growth. Well, in this case, that's the 2n squared needs to come first. So we end up with f of n is equal to 2n squared plus 2. Okay. Now it says only keep the biggest factor of n as it approaches infinity. Well, we only have one factor of n, so we don't have any change here. So only one factor of n, so we still keep our 2n squared there. But the final step says take away any constant values and coefficients of n. So let's get rid of, oh, I made a typo in my PowerPoint. Just give me 1 second. There we go. There we go. So the first thing we're going to do is we're going to get rid of that plus 2. So we have 2n squared, but that's because we removed the plus 2. That's a constant value, gone. But we still have a coefficient of n, and that's that other 2. So we have to remove that, because both of those are insignificant as n grows to infinity. I know it's counterintuitive. You're like, but it's doubling. It's doubling. It's doubling, and that double makes a difference when 10 gets doubled to 20. But when you're so big, and n is approaching infinity, where we don't even have names for the numbers, that 2 means nothing, because we can't tell the difference. We have no difference. So all said and done, we have f of n is equal to n squared. So that means that our final algorithm runs at big O of n squared time. Now, once you do a little bit of research online, you're going to find out that there's other forms of notation as well. There's things like big omega and stuff like that. And all those are the same idea, but a different target. Big O is all about the worst case scenario. So if everything went wrong, for example, let's say it was a searching algorithm and it couldn't find the data after it checked every single element. That's the worst case scenario. The best case scenario is that it finds it at the first place it checks. The average case scenario is it's somewhere in between. So there's 3 different notations that we look at. There's big O for worst case scenario. There's big omega for the best case scenario. And then there's another one for average case, which I can't remember off the top of my head. But we're going to focus on big O of n squared. So what I want you to do on the next slide is try this out. Now, if you're working at home right now, which you probably are, try and grab a friend and do this on Discord and have a quick little discussion, Discord or whatever the popular technology is that you're listening or that you use right now to communicate with your friends at this point in the course, whenever you're listening to this thing. So I want you to break this algorithm down and tell me what the big O notation is. What's the final time complexity of this algorithm? So I'm going to say pause the video, go do that, and then come back. When you're all done, you can come click on this little answer here. Say, click here for the answer. All right. And we're back. I'm going to hope you're back now. So we click on this, we end up with, it's not a big O of n squared algorithm. And why? Because the data set this time is non-square. We have m by n, so m rows, n columns. So what that means is the first loop is going to loop m times. The second loop is going to loop n times. So the data in between is not n squared, it's m times n, which means when we're all said and done, we end up with big O of m times n. Okay. And the M is not insignificant now because it's actually dependent on N. So everything is factored together. So it's a multiple. It's not just a literal value. Okay, great. Now there are a lot of common time complexities out there for operations that we do a lot. So in this mindset, it may just be easiest to memorize these things, but I don't actually recommend that, because if, for example, you are ever asked to explain something, just telling somebody the answer doesn't show that you actually have that knowledge. It shows that you can recall something. It doesn't mean you can actually determine it. The thing is, your algorithms that you're going to be using going forward in your career are not just going to be standard algorithms all the time. You're going to be writing new stuff, things that other people haven't written before, because there's different solutions to different problems. You need to be able to break down your solution or somebody else's solution and compare them to say, let's use your method. It's better than mine, or vice versa. So let's look at a couple common operations that we do that we need to keep in mind when we're talking about time complexity. So the first one is nested loops. Now you already saw this. So this implies a cost of the size of the outer loop is multiplied by the cost of the size of the inner loop. And anything inside happens that many times. So we have big O of m times n, or big O of n squared, depending on the size of each loop mechanism. So then we get into the other one, another big one, which is called divide and conquer algorithms. Now we've already talked about this earlier in the course. So these are algorithms that divide the data in half continually until a single element is left. This is super common in recursion. Now we're actually going to cover a number of different elements or data structures, not data structures, but a number of different concepts going forward in the course that are going to use this divide and conquer strategy. We've already talked about one earlier on in the course. So these algorithms run at big O of log n to the base 2. Typically we just write this as big O of log n. We just ignore the base 2. Again, note that log has a base 2, not 10. In your math class, you're used to everything having a base 10 when you're dealing with logs. For this, it's a base 2. And to generalize and simplify this way too much, this is basically due to the constant division in half. We're dividing it by 2 every time. Okay. More on this later on when we talk about merge sort. We'll actually get into the math of it, and you guys can break it down from that point. So if you want to know more, and there's more common complexities that you want to look into, things that you just want to know off the top of your head, click on that link there. It's going to take you to kind of like a cheat sheet that discusses tons of algorithms and tons of efficiency discussions. Now, efficiency is time and space. This whole discussion was all about time complexity. There's another area completely about space complexity, and that's all about how much extra data that you use for your algorithm, right? So if your algorithm doesn't require any extra data and it does everything right on the spot, that's great. That means you're not using anything unnecessary. However, there's some algorithms where it might double, triple, or even more, square even your data set that you're working with. So we got to be conscious of this. And recursion can sometimes be very guilty of this due to things like the call stack and stuff like that. Okay, so that is time complexity and everything we're going to talk about. Your homework is a little bit different this time, so you're going to be analyzing an interesting algorithm called merge. Good luck with that, and we'll see you next time in class.